I'm going to model the first of a couple of mechanisms which draw an interesting little curve called the harmonic trinodal curve. These are interesting algebraically because if you think of the equation of an ellipse or hyperbola, which would be x squared over a squared plus y squared over b squared equals 1, or x squared over a squared minus y squared over b squared equals 1. These harmonic trinodal curves have that upside down. They have an equation a squared over x squared minus b squared over y squared equals 1, or a squared over x squared plus b squared over y squared equals 1. Anyway, let's have a look at the mechanisms required to draw such a curve. And as usual, I'll be using GXWeb. So for the first of these mechanisms, we need an auxiliary line which the mechanism constrains to be vertical, but is going to be able to move left and right. So we'll constrain this thing to be vertical by making it perpendicular to the x-axis. And then there's a little crank that's going to drive the thing, and we'll give that length a. Now there's also a link that joins the meeting place of this vertical line with the x-axis up and comes back onto that line there. Now this line is kept to be perpendicular, and these two are constrained to be perpendicular. And then length DE is constrained to be length B. Well, here we run into a problem. GXWeb is not going to let us constrain that length. It's not able to figure this thing out itself. So we're going to have to give it a bit of a hand. A good thing to do at this point is to find something that GXWeb will let us constrain. So it will let us constrain this length, CD. So let's constrain that now. Let's not make it B because DE wants to be B. So let's make it C. And now we can ask, what is the length of DE? C sine theta naught. Well, there's no theta naught in our drawing. Let's make sure stick an angle into our drawing. We do want to be making it AB turn round. So let's just look for that distance again. Oh yeah, theta naught really was theta by the look of it. So in order to make DE equal to B, we should have, instead of C, we should have C over sine theta. We've got a 90-degree theta there, which is not particularly useful. Let's make that something other than 90. And now let's just look at distance DE again to make sure it's doing the right thing. Distance DE is in fact C. We really wanted it to be B, didn't we? So let's make that B over sine theta. Final check. There we go. Distance DE is B, so we have the model we wanted, and we can now trace the point that's going to trace the curve, which is in fact not this point D, but this point E here. So let's trace that as theta varies, and we get our curve. We can do some varying of that by varying A with respect to B. Watch how that thing changes. And we can ask for its equation. As you notice, if it's a fourth order curve, if we divide that curve through by x squared, y squared, you're going to get x squared, a squared over x squared minus b squared over y squared equals 1, which, as I said, is a hyperbola kind of turned upside down in a particular way.